2's complement is how computers represent negative integers. You might know that computers store bits, but numbers are not just bits. And 2's complement is the way we handle negative integers. I believe it's one of the most mistaught concepts in computer science courses. You always hear people talk about 1's complement and do this weird +1 trick, and you might wonder how people could ever think of doing this. If you were frustrated like me, this video is for you. Imagine we're in an alternative timeline. It is the Christmas of 1968, and your dad just bought you a pocket calculator. Since we're so far back into computer history, the calculator is kinda terrible, and it can only operate on 2-digit numbers, from 00 to 99. It also offers a limited selection of operations, only 2 of them, addition and multiplication. Honestly, not very useful. But it can tell you that 12 times 7 is 84. What if the result is larger than 100? Out of curiosity, you try 12 times 12, which turns out to be 44. What? It turns out that this calculator is lazy. If a result has more digits than supported, they're ignored, chopped off, and only the last 2 digits are shown. The calculator can only display 2 numbers, and it refuses to show more. So, in the lazy brain of our calculator, 12 by 12 is equal to 44. We will write a lazy above the equal sign to denote this. If we try 28 by 23, the lazy calculator thinks that the result is also equal to 44. So, in the calculator's eye, these 2 multiplication formulas are the same. But we clearly see that they are different. Differ by 500, in fact. You see, the lazy calculator considers 2 numbers equal if they differ by a multiple of 100. This is because when you chop off some digits to keep the last 2, you always chop off a multiple of 100. Next morning, you want to find out how many weeks are there in a 31-day month. A week is 7 days, so you want to calculate 31 divided by 7. Since you just got this fancy little box yesterday, you naturally want to use it. But sadly, it cannot do division. So you thought of an old method, subtracting repeatedly. You see, 31 days minus 1 week is 24 days, minus another week is 17 days, minus another 10, and then 3. 3 is less than 7, so our original 31 days is 4 weeks and then some. However, you just realized that your calculator cannot do subtraction as well. You read the manual of the calculator, which said, try adding 93 to stuff and see what happens. Desperate, you turned the calculator on, entered 31, and added 93. The number that popped up is 24. And then you added 93 again, and got 17. Same thing, and 10, and then eventually also 3. But why could you subtract 7 by adding 93? You see, every time we add 93 to these numbers, we got something slightly higher than 100, and then we chopped off the 1 to the left. We basically added 93 and then subtracted 100, and the net result is just subtracting 7. So, for this purpose, we can say that 93 is basically negative 7. In the same way, 94 is negative 6, 95 is negative 5, and so on and so forth, and 99 is negative 1. Then you got curious. The calculator has another operation, multiplication. Would our newly discovered negative numbers also work in multiplication as well? You tried it. What's negative 1 by negative 1? It's 99 by 99, which lazily is equal to 1. What's negative 2 by 3? If we do 98 by 3, the screen reads 94, which we know is negative 6. In general, if we multiply 2 negative numbers together, let's say negative x by negative y, in the calculator, we will enter 100 minus x times 100 minus y. It will be 100 squared minus 100 times x plus y plus x times y. The first 2 terms are multiples of 100, so they get wiped out by the calculator, and the only term that remains is xy. Our definition of negative numbers just recovered an arithmetic law. We earlier said if two numbers differ by a multiple of 100, the calculator will think that they're the same. We have just extended this rule to negative numbers as well, and we showed that this works with addition and multiplication. Mathematically, this structure is called integers modulo 100 or mod 100. And when you do this, addition and multiplication are preserved for positive and negative numbers. Mathematicians use the z symbol for integers, the slash symbol for modulo, and integer mod 100 is written as z/100z. For the lazy equality, mathematicians use this symbol. If we list all the integers mod 100, we will start from 1, 2, 3, count all the way to 99, 100 which is 0, and then 1 again. The numbers loop back to themselves, like a circle or a ring. In abstract algebra, this kind of structure is therefore called a ring. As a convention, people give names to these numbers. We call the smaller numbers 1, 2, 3, and the largest numbers -1, -2, -3, and so on. We split the numbers down the middle. Positive gets 1/2, negative gets 1/2. If we look at the other end of the circle, 49 will be just 49, 51 will be -49, but what's 50? We decided that 50 is named -50. Why? This will make it easier to tell whether a number is negative. You just look at the first digit. 5 through 9, negative. 0 through 4, positive or 0. It's important to know that this system of giving names to numbers is just a convention in our head. It doesn't matter if the number goes by 93 or -7. It does the calculation anyways. Calling a number by a different name doesn't change how it behaves. There's one more hack. How do we find the negative of a number? Mathematically, we just subtract it from 100. But the subtraction is going to be a lot of borrowing, and we hate subtraction with borrowing. The hack is like this. 100 is just 99 plus 1. So 100 minus x is 99 minus x plus 1. Subtraction from 99 is very easy. You can do this digit by digit and don't need to worry about borrowing at all. We can then add 1 to the final result. So -42 is 57 plus 1 or 58. Alright, in the hypothetical story, everything happens in decimal. In the real world, this process happened with binary. Early CPUs are really simple. You can think of them as binary calculators with addition and multiplication. Many of them are 8 bits, so the numbers range from 00000000 to 11111111 in binary. We usually refer to them as 0 to 255. Just like us with the calculator, early computer scientists are trying to find a way to calculate on negative numbers and figure out the same thing that we have done before. They assigned half of the numbers to be 0 through 127 and the other half to be -128 to -1. Again, addition and multiplication works nicely with these names. In our decimal system, the highest digit will serve as both the tens place and the sign. Now in binary, the highest bit represents the sign only, so it's called the sign bit. Now, how do we get the negative of a number again? In decimal, we subtract from 99 and then add 1. In binary, the row of 99 is replaced with the string of all ones, also the largest number. So, we take the all one number minus x. That is virtually just flipping every bit. Zeros become ones, ones become zeros. That's the easy part. But just like in decimal, we're short by 1. So we add the 1 back in. Flip the bits, add 1. It's not magic, it's just 100 minus x in disguise. For historical reasons, this system is known as 2's complement. But for me, it's just the most natural way to do positive and negative arithmetic on a calculator. Or on a CPU if you like. Thank you very much for watching this video.